Here's a data set of faces. Now, take one of them, and let's see how you can represent it. Now, if the data is, and the data doesn't even have to be well normalized. It can be different lighting conditions, slightly different orientations, slightly different facial expressions. And we're just going to use pixels to represent the data, right? So I'm going to take, if this bitmap is k by k, I'm going to take each pixel and use that as an attribute. So I'm going to have a k squared total pixels. Now, to use PCA, your data, each instance, need to be represented as a vector. So what I'm going to do is I'm going to take this bitmap, which is a k by k matrix of pixels, and I'm going to unfold it into one long vector. So what that means is I'm going to take the first row and sort of unfold it as part of the vector. Then the second row is going to go below it, and then the last row is going to go at the bottom. So it's going to be a pretty big vector. It's going to have k squared components, but it's going to be a normal vector. Now, I can then just take PCA and run it on a collection of these vectors. So I'm going to have one of those vectors for every single face in my data set. So overall, my data set is going to be a k squared by n matrix, where I have n faces, so n columns, and k squared rows, one for each pixel. After I run PCA, I'm going to end up with a set of eigenvectors, and I'm only going to take m largest eigenvectors out of. So the total number of eigenvectors in this case is going to be k squared, right? Because that's the dimensionality of the covariance matrix. But I'm only going to be looking at m smallest ones, right? So what comes out of PCA is going to be a matrix which has k squared rows, because each one of the eigenvectors is going to be k squared dimensional, and there's going to be m of them. Now the cool thing about these is you can take each one of these and fold it back into a matrix form. Each one of these vectors is k squared dimensional. So if I take the first k values and make it the first row, and the second k values make it the second row, I can fold the vector back into a form that looks kind of like a matrix, and you can visualize it. Because the numbers that you're going to get, you're basically going to get a picture that had the same dimensions as the original picture. Only now the numbers are going to be positive and negative, so you're going to need to shift it a little bit. So in this case, it's shifted towards, I believe the negative numbers are the dark areas, and the large positive numbers are the light areas, and sort of the grays are sort of in the middle, closer to zero. So that's, if you did that on a collection of faces, this is what the top eigenvector would look like. That's the eigenvector with the largest eigenvalue. And you can look at that and you can basically get some idea for what's important in the data. Right? It's certainly not a face, but it tells you something interesting. Right? If you look for the areas which have the whitest and the darkest regions, so the whitest regions tends to be around the face. So what is that? That's hair. What that means is the biggest factor that differentiates people's faces is the hair. That tends to be the dominant thing, that tends to be the component that dominates the variance in the data. And then it's a bit of the eyes, and then you have very dark areas under the nose. And that's because some of the guys there have a mustache, and some of the guys don't, and the area looks very, very different. So you sort of have a binomial, you have a bimodal thing, right? You've got guys with a very dark patch and guys with a very light patch, and that contributes to a large amount of variance. So the way to interpret that is what factors, what features of a face seem to contribute to the most variance that you have in your data. And that, of course, is just the first eigenvector, and if you compute a bunch of them, so there's, I believe, 25 of them, right? That's the first one, and then you've got others. So they're focusing on progressively different regions of faces, the bright spots. They're highlighting sort of the dimension of variance that that particular eigenface is capturing in your data. So